right, I guess we're getting very close to 7:30, which is when the presentation will start. Just a brief mention, next month's meeting will be, in addition to having the election, we will be having a guest presentation there on Friday, May the 13th. I got to look at my email correctly. I got to find my notes, bear with me. So yeah, next month's presentation is, the guest presenter will be a UW graduate student named Rachel McClure, and her topic is going to be formation and maintenance of galactic bars in local disk galaxies. Where do they come from and where do they go? Sounds like a lot of a really fun topic. Also tonight, I'm going to go ahead and introduce what tonight's presentation is all about. We have Devoured Worlds, the search for planet-ingesting stars in open clusters. Tonight's presentation is about the observational signatures left behind when stars consume their close orbiting planetary companions, the ways we're searching for these events, and why finding cannibal stars in open clusters is critically important to our understanding of stellar and planetary astrophysics. This is presented by Dr. Melinda Soares-Furtado. I'm sorry, am I saying that right?
It's Soares-Furtado, but I would never ask anybody to do that. So Soares-Furtado is perfectly fine.
Sorry to butcher that. You know, when I was in the UW marching band, we had some students that were of Norwegian descent, and I don't know how Michael Leckrone got through awards night and was able to say every one of their names absolutely perfectly. It's an amazing talent, which I don't have. So a little bit about our guest speaker tonight, Melinda. She is, pardon me a moment while my phone's ringing. Oh, now that just blew my train of thought. Okay, Melinda is—
You have Cricket Wireless?
Yeah. Melinda is a NASA Hubble Postdoctoral Fellow at the University of Wisconsin-Madison. She has a Bachelor of Science in Physics from the University of California, Santa Cruz, and a Ph.D. in Astrophysical Science from Princeton University. She works on detecting and characterizing stars in open clusters that have anomalous characteristics brought about by the ingestion of close orbiting substellar companions. On behalf of Madison Astronomical Society, I'm delighted to present to everyone Melinda. And oh yeah, are you ready to go? There you go. There you go.
Okay, great.
Nice to meet you.
Thanks so much. Yeah, no, I'm so glad to be here. Thank you so much. It's great to connect with the community here in Madison. So my family moved here not too long ago. I just finished my PhD in 2020. And so, yeah, it's great to just get connected. And I don't know, these astronomical societies, there tends to be just so much heart and talent and interest. I remember the last time I gave one of these talks, I met people that were like building their own observatories and knew more about the night sky than I did just looking up at constellations. So it's humbling, and you know, please don't try to stump me because you will. I'm very good at my niche, but yeah, don't have a map of the night sky in my mind. But that being said, I'm happy to talk about something I've spent a lot of time thinking about, which is planetary ingestion and planets around stars at late times. I've been more recently thinking about them at very early times as well. So the sort of common theme for me these days is turning away from this main sequence, this hydrogen burning sort of steady state life cycle, and thinking about early stages and late stages. But I'll be talking more about the late stages today, and the fact that planets do many times become engulfed, and that in fact that's a fate awaiting many systems, in fact our own rocky bodies included. You know, not for quite some time, but it's interesting to see if we can actually find some of these systems. So with that, I'm going to go ahead and share my screen and start off with a little sort of theatrical animation. And this is just sort of just a silly animation of what happens when a star is starting to run out of hydrogen in its core and is no longer in the condition to really hold itself up against gravity by that nuclear fusion process. And so it must begin to fuse heavier and heavier elements. However, in those heavier element fusion processes, you create much stronger temperature gradients. And that strong internal temperature creates a response in the star adiabatically by it expanding in size. And so in the case of our own sun, it'll become 200 times as large as it is at this current moment, and will engulf most certainly Mercury and Venus, and depending on tidal effects, perhaps even the Earth. So it is a fate that accompanies something like 30% of all sun-like stars at some point in their life. They're going to engulf some companion. And one of the questions that I became interested in while I was at Princeton was thinking a little bit about what sort of signatures do these events leave behind? What sort of time scale is this process happening over? Is the luminosity of the star changing? Is the rotation of the star changing due to like angular momentum transfer? These sort of things became very interesting to me. And can we go out and look for definitive proof that this has happened? And what we end up finding is the answers are going to be, I'm going to show you and not just tell you, yes, there are these signatures that are left behind, that they can last quite a long time, that they can be statistically significant in many cases, and in fact can tell us things about what planets are made of and where and how they form, which is really phenomenal, that from the sort of death throes of this cannibalistic event, do we learn about these early formation processes that otherwise we really wouldn't have the same sort of window into. We can contrast this, for example, with James WST, the new telescope that's been launched at the second Lagrangian point, that will tell us all sorts of things about the outer chemical composition of atmospheres. But if you really want to know what cores are made of, the depths of the planet's interior, what those sort of compositions look like, there's really no other way than to actually disassociate those particles and either rain them down on some star at very late times, or to ingest them and then look at the photospheric signature of that star. And so that's sort of a too long didn't read intro, and I hope to now sort of compel you with some actual data. So first off, I want to just start by talking about the current exoplanet census demographics, which are probably not all that new to you. I'm sure many people here know that we just passed that 5,000 mark in terms of the number of known confirmed exoplanet detections. And so even in my own lifetime, and I'm, for a postdoc, a little bit older returning student, I have grew up at a time where the only planets that we knew of definitively were those in our own solar system. And I have seen, as many of you as well have, just this incredible transition as we have perfected techniques for detection, as our techniques have been accompanied by an ever increasing sensitivity in terms of spatial resolution and signal to noise. And we've really seen this incredible dawn of the exoplanet age, where nearly every star in the sky we now know to be accompanied by an exoplanet, and that those exoplanets can show up in all sorts of interesting architectures that can differ wildly from what is found in our own solar system. So it's quite fascinating. But for all that we know, what I'm going to show you in the next couple slides is we know about a very specific type of host star and a very specific type of planet, meaning that there's still a lot more to learn. And so in this plot, we're just looking at the count. Can you see my cursor okay? I don't think you can. So I'm going to describe what I'm doing here. On the y-axis, we're looking at just the cumulative count. So we're just sort of adding them up as we go through time, and we're starting here at 1990. We have some of these very, mid-90s early detections, and we're going all the way up until March of 2022. So this is just last month redone this plot. And we see at that first white vertical dotted line, the launch of Kepler in 2009, where we're starting to get a really strong spike now in the detections. And in 2018, Kepler is being decommissioned. It was called K2 at that point. It's neither here nor there. But with its decommissioning, we also saw the launch of TESS, which has continued to bring in just an incredible wealth of discovery. And so the next plot I want to show you is really to drive home the fact that the transit technique, the idea of looking at the brightness of a star and how it changes with time and seeing some periodicity in that signal, has really been the leader in terms of the detection methods. So radial velocity information has provided a lot, and there are all sorts of other ones that you've probably never heard of. I know some of them were new to me not very long ago, that have played a much more minor role. But transits have really led the race here, and have continued to do so even today. So that's really how we're learning about these star-planet systems. And here I'm plotting just a color magnitude diagram. So we're showing really it's in luminosity effective temperature space here for you, giving Gaia information to infer those properties. This color bar here is showing you the surface gravity, which tracks, it's a really nice probe for the evolutionary state. Maybe I do need a nice cursor so I can show you the main sequence. That diagonal line that is going through that luminosity temperature space is what makes the main sequence. So stars on that particular point of the plot are burning hydrogen in their core, just sort of steady state. They exist, you know, our own sun, 90% of its lifetime is going to be just sort of sitting, burning hydrogen in its core. Its mass is not going to change very appreciably. Its luminosity is not going to change very appreciably, nor will its temperature. But there's a rapid departure, which you see as you turn off of the main sequence. This is the stars that are becoming sort of cream and then orange and then bright red. That's showing this drastic reduction in surface gravity because the object is now so extended in size. It's this sort of low density, large ball of plasma. And you'll notice by just looking at this plot, most of the stars that I'm showing here, these are all stars that have confirmed exoplanets. Most of them exist on this main sequence. And that is by design how the instruments are looking for these objects, because as you can imagine, these very extended, bright, luminous stars, you're going to have much smaller contrast ratios when you have a Jupiter-sized object passing in the line of sight of that star. It's just harder to detect those objects. There's also one lone white dwarf detection you'll see down there, 1856 plus 534, that was detected by Andrew Vanderberg, who was a professor here at UW-Madison last year. And that was actually a planet that's larger than its own host star, similar to what Bob Aloisi was talking about earlier. This is the kind of work that he's doing. So we'll start to see, I think, also that bottom left-hand part of the plot, these late stage systems, which have blown off half a solar mass worth of material, and now have these planets that are orbiting around them. There's all sorts of interesting open questions about whether they survived an engulfment process, whether there's late stage formation of planets, you know, how they sort of got to be so close to these objects that have gone through such dramatic increases in size. And so in this plot, what I want you to take away from here is that most of these objects are on the main sequence. Most of these stars with exoplanets that have been confirmed are, again, happily burning hydrogen in their core, sort of, you know, middle-aged objects. But let's break down what that means by numbers. So I just take all of these objects and show you in a pie chart. Objects that I would consider a main sequence are things that have surface gravities above some number, which is 3.5 dex. It's neither here nor there. This is how the cutoff that is similar to when things are turning about white in this plot. So as you can see, they're sort of turned off the main sequence and going up that cream red sort of luminosity spike. So we've broken them up in this way. And 4.2% of those 5,000 confirmed exoplanets are really objects that are late stage objects. These are objects that are beyond hydrogen burning in their core. They're either burning hydrogen in a shell, or they're burning core helium. There's some later process going on where they're extended and it's much more dramatic. So all this is to take away the fact that while we know of a large collection of bodies, and you know, we know more than we ever have before about those sorts of architectures, there's still a lot to learn about the sort of architectures and systems that are orbiting stars at later stages. The same can be said about earlier stages, but I'm not really going to go into that too much here, but we know just as little. Okay, and let's see if I can move. No. Can you? Oh, yes, you can see it. So if you notice here, I'm showing now a cumulative stacked histogram next to this pie chart. It's the same histogram as we showed before, just the count going up as a function of time. But I've really broken them up into the two groups now. I've broken them up into the main sequence objects shown in blue and your late stage stars now shown in this sort of salmony color. And you can see it's been sort of a steady monotonic increase with time. Starting about 2010 is where we really start bringing those ones in. But it's not like there was one mission in particular that really revealed all of them. It's just been sort of a slow aggregation of these systems. And this is because we also don't have instruments that are specifically focusing on trying to find planets around these late stage stars. So this will continue to be an issue until we can really think about, you know, designing surveys for this very purpose. Similar things can be said about these early stage objects. where if you wanted to find planets around very early type stars, sorry, early stage stars, meaning that they're 1 million years old, 2 million years old, you really do need to think about different instrument design. Primarily more like infrared information is really what we'd want. And of these particular systems that I'm showing you, again in blue, the main sequence, and in salmon, these late stage systems, I'm giving you now in this histogram, just the host mass. And what I want to reveal here is that most of the types of stars that we're looking at are not only these sort of middle-aged, run-of-the-mill hydrogen-burning objects, most of them are very sun-like. They're about 1 solar mass. And so you can really see what looks almost like a Gaussian distribution around this 1 solar mass marker. And for the host stars, there's a slight offset from that, which may be kind of peculiar at first. But when you think about the fact that stars that are lower than, I don't know, 0.7 solar masses haven't have enough time in the age of the universe to use up all of their hydrogen core fuel, that offset is expected, that you really are going to be biased towards objects that have quickly ran out of that supply. And the more massive an object is, the faster it goes through its hydrogen supply. So that shift is not completely unexpected, but it's also not all that different than that 1 solar mass, because the contrast gets harder and harder the more massive the object is, because its size is so much larger. So again, not totally unexpected. And here we're going to be plotting the same objects, but now I'm showing on the x-axis the orbital separation. So this is a distance in AU, where 1 AU is just the distance between the sun and the Earth. So this is that orbital separation of stars and their planets that we know of. And surface gravity is again shown, where anything above that 3.5 is a main sequence. So think of blue and blue-white being main sequence. So nearly everything here that we're plotting, that we have this sort of information about, surface gravity information and planetary radii, are all main sequence stars. And on the y-axis, I'm showing you the planetary radius of the object that are orbiting these main sequence stars. So not only are most of these, again, main sequence, most of them are close by. They're within this red region known as where hot Jupiters would exist. So this is something below 0.1 AU. So these are incredibly inhabitable, close orbiting systems that are more privy to the transit technique, just because you have a greater probability of observing them if they're close to their host star. And a lot of them are very large in size. So this is another issue. Oh, I'm noticing it says radius and I have a M instead of R. Okay, good job, Melinda. Make a little note for myself. Okay, so most of them are, Jupiter size. We don't have a whole lot much below an Earth-sized object. And there's this thing that's known as a radius gap. You kind of might notice there's a hole in between 1 and 10, Jupiter radii, where there's just a lack of objects therein. And there's a lot of conversation as to why that might be, whether or not you're actually evaporating envelopes, or there's 2 different formation channels that are perhaps happening there. But again, when we're doing these sorts of analyses and we're talking about radius gaps and what sort of objects we can find, we're talking about them around sun-like middle-aged stars. And that's really a limiting scope to frame a lot of these questions. I'm gonna hope to illustrate an assembly of objects that have been observed. This is basically a simulation showing the orbital separations relative to one another and the sizes of the objects in their radial extent. And this was updated in September of 2021, so it's pretty recent, to give you a sense of just sort of a vast type of architecture, a vast type of different sizes that we have. But yet again, to just make the point that for all of this diversity, there still is a lot of limitation in terms of the host object in question. But I think that is going to change. And I think that the next chapter is going to entail sort of broadening the scope in terms of the types of stars that we're looking at. And what I'm going to hope to compel you with the next couple of slides is why that is a valuable thing. Not just we should be observing them because we haven't been, and we should fill in that parameter space, but to hope to really compel you to think about the intrinsic scientific merit that these objects also have to share. Okay, so again, we're going to talk in this next section about some of the anomalies that ingesting a planet can induce into their host stars. And then I'll talk a little bit about why open clusters have been the place where I am looking for signs of these ingestion events. Open clusters and more recently co-moving groups, which can span a wide variety of ages and be quite a bit younger. So I've sort of expanded the populations that I'm looking at, but open clusters are sort of the primary place that I look these days. And so we're focusing in for this particular presentation, again, on these low surface gravity objects that I'm going to call post-main sequence. So they could be, again, in the subgiant phase, in the giant phase at various points. And again, reminding everyone that, there's still a very small sample size here. So in this particular plot, that's about 200 objects out of the 5,000 confirmed that we're able to take account on. So I also want to convince you that engulfment is a fate awaiting many, many systems. And so in this particular plot where I'm separating post-main sequence and main sequence in this surface gravity space where everything, again, greater than that 3.5 is what we'll call a dwarf star or a main sequence star. I'm going to use these terms interchangeably. And everything above that in that peach region is this post-main sequence. And here I'm plotting just the orbital separation of known confirmed exoplanets in exoplanet.org. And this dashed or dotted vertical line is showing you that hot Jupiter cutoff at 0.1 AU that people typically talk about. And what you might notice is in the upper left-hand region, there aren't a lot of objects, right? It's sort of empty in terms of close orbiting objects at these late stages of stellar evolution. But hopefully this red, blue, and green line are going to show you why this is to be expected. So what I'm plotting here is I'm using a stellar evolutionary code called MESA, and I'm plotting as a function of time, basically the size of the star. I'm showing it in AU, akin to that orbital separation. And what is happening is that star is expanding as it is going, as it's getting older. And any object that would be leftward of those lines, any planetary companion that would be shortward of that radial separation would be inside the planet, would be engulfed. But these objects at this bottom left-hand corner, which are primarily orbiting sun-like stars, remember that distribution shows that most of these host stars are not unlike our own sun, those objects are going to shift to that upper left-hand corner because their stars are going to evolve and they are going to expand to be 200 times the size they are now. And what is going to happen is that the eventual fate of those objects in that bottom left-hand corner is the top left-hand corner. This is where they are going to show up. So it's not surprising that it's empty in that top left-hand corner. And the ones in these bottom left-hand corner that are shortward of that dashed line, they're doomed. It's a matter of time. Of course, these things are happening over much longer timescales than any human being should be worried about. But when we're thinking about astronomical timescales, they're most certainly doomed. And so one of the things that I wanted to think about was, let's play a simulation, let's play a toy model and ask ourselves, what happens if we take a sun-like star, which I'm showing in this schematic in the left, I'm depicting the core and then its radiative zone that surrounds that core, and then its outer convective zone, which is about 1/3 in depth of the entire star. And we have a hot Jupiter, and these things are shown relative and in appropriate sizes. And with time, the object does expand, it does engulf this hot Jupiter. What happens in terms of the chemical signatures? Is the chemistry all that different when you ingest a Jupiter's worth of lithium and other elements? And would that information be statistically significant? So maybe there is a change, but is it so negligible that it's statistically, not a signature worth looking for? So that's something I'm going to show in the next couple of slides. So again, the main question that was driving this is from the perspective of the host star, is exoplanetary ingestion a negligible phenomena? And more specifically, what are these observational signatures that are expected, and are they statistically significant? So I'm going to go through just a couple of them. We're going to focus on chemical abundance anomalies because that's the one that I find most interesting, but I think it's important to sort of give an overview of these 4 smoking guns that are expected to accompany the cannibalization of a planet. One of them that I worked on with some folks over at the Flatiron Institute in New York City was the idea that there's an appreciable amount of energy that's being liberated when a planet is being ingested. It's basically its orbital energy is being liberated into the star. And where does it go? Can we expect there to be an optical, UV, or X-ray radiation spike? And how much energy is being liberated? What's the sort of strongest spike that you might expect if all of that energy went into visible light, for instance? You can also expect that with that angular momentum transfer and that energy transfer, you might be able to eject or strip material from that outer stellar envelope. So you might expect some infrared excess or mass around that star in sort of a circumstellar environment that perhaps you could pick up with an infrared detector, for instance. You also might expect changes in angular momenta. I talked about angular momentum transfer, and there's lots of studies that are being done to show that you can actually enhance rotation pretty significantly. You might even be able to have stars that are rotating an order of magnitude faster than you'd expect. Some of them even are able in simulations to reach near critical velocities where they're almost going to be unbound at this point. They can't even support themselves with their gravitational binding energy anymore. And then lastly, the chemical abundance anomalies, which is not really straightforward, because if you think about the mass differences here between Jupiter and the sun, you're thinking about 1,000 times difference in mass here. What sort of chemical fingerprint is that really going to leave, and can we even hope to observe that? So the first thing I mentioned was that energy spike. How much energy and where does it go? And so in 2018, I worked with Morgan McLeod and Matteo Cantiello to look at how much orbital decay power is going to be liberated as this object is inside the stellar envelope and is decaying its orbit and losing that energy and liberating it to the star. And we compared it in this plot, which is another color magnitude diagram, to the intrinsic luminosity of the star. And we did this for various types of stars. So here we see, stars that are 10 to the 8 years old, 10 to the 9 years old, 10 to the 10 years old. And we did it for all sorts of different companions, but I'm showing in this plot what it looks like if you eat a Jupiter. And what we found is at these really bright regions, which are not too far off that main sequence turnoff point, which is that point where it's running out of hydrogen in its core, that you actually can be liberating 10 to the 4 times the sort of luminosity that is intrinsic to the star. So if you're taking how quickly it takes to decay in terms of its orbit and how much orbital energy it has, and you treat that as a power, you can compare that to the output power of the star, and it is 10,000 times greater. So there's a lot of energy, but where does that energy go? That question is not answered by our work, only that there is a lot to liberate. And that indeed, if it went into luminosity, you would expect a detectable photometric signature, if that is what is being done with that energy. But there are a lot of unknowns. A student that I've been working with at UC Santa Cruz, Ricardo Yarza, has been working on whether or not you can inject material. So I talked about one of the second smoking guns being liberating this actual envelope of the star, which you would see as infrared excess. So in this plot that he's showing from one of his papers, we're looking at the orbital separation again on the x-axis, and on the y-axis, we're looking at the mass of the companion as it compares to a Jupiter's mass. So at the center, sort of midline on the y-axis, we're seeing 10 times a Jupiter-sized object. And at the very top, when I say 100 times a Jupiter-sized object, we're now in sort of brown dwarf terrain in terms of mass. And what he found is that it's very difficult to eject the envelope. So only in that upper right-hand corner are you actually able to eject the envelope. What this means is you need objects that are nearly brown dwarf massed. They got to be pretty great. Jupiter's not going to be able to do it. And they need to be pretty far from their host star when the engulfment process begins. And that makes a lot of sense as well, because you have a longer lever arm for your angular momentum transfer there. So there's just a greater torque that you're able to induce. And so your hot Jupiters are going to be safe. They're going to make it down into that convective region and be destroyed therein and deposit their material in that region. And only in those more distant places where objects are very massive do you expect a significant amount of stellar envelope to be ejected, which is really good for me to hear, because it means that looking for nearby orbiting hot Jupiters that are being eaten by their stars, looking for chemical fingerprints does make sense. That material should be in that convective layer and should be observable. So again, the takeaway is if you want to eject the envelope of your star, you have to be a pretty massive substellar companion, and you need to be able to intercept it in terms of being ingested once that star is pretty far into its evolution. So it needs to be into mid or late giant stages. This is going to happen near the main sequence turnoff when the energy when the star is still not so extended. But what about spin? Is spin something we can look for? So we can see stellar spin in radial velocity data by Doppler broadening. We can see stellar spin in photometric information, which is a way that I typically look by just seeing star spots that are passing in and out of view as the star is spinning. But would we expect there to be any kind of appreciable divergence from spin? So I worked with a student, Tyler Barna. He's now at the University of Minnesota, but he was an undergrad at Rutgers at the time. And we looked at one particular cluster called M35, and we measured rotation periods of the stars in this cluster. And what you find is that this is true for all clusters. You get a nice sequence in period versus color, which can also be mapped onto, period versus magnitude, which can also be mapped onto mass, because at a common distance, that magnitude difference for that common system basically corresponds to there just being different massed objects. And what you see is you get that nice sort of tight sequence that's shown there in the blue, where objects sort of behave pretty linearly in this relationship. And the older you go in a cluster, and this is a pretty young cluster, it's like 150 million years old or so, the older you go, the tighter that convergence becomes. But you always find these sort of outlier objects, which I have circled in red here. These are objects that are rotating more rapidly than would be expected by this gyrochronological sequence, is what we call it, or period magnitude mass relation. And those objects were kind of odd. And do we know that they're rapidly rotating because they ate a planet and that planet imparted angular momentum? Not outright, but if it also had weird chemistry in a way that you might expect, we also saw signs of planetary composition. Okay, now we're starting to talk in a more interesting way, where there's different pieces of evidence that point to a progenitor pathway. And this is how in clusters we're looking for signs that we have a candidate for ingestion. We're looking for these rotating outliers, and they're pretty easy to find, especially as you get older in clusters. So the clusters I'm looking at the moment are 2.5 billion years old and 8 billion years old, where this sequence is incredibly tight, and these outliers very much stand out. Okay. But how much change do you actually expect in stellar spin? So I'm not a dynamicist and I don't work on these dynamical models, but I think it's important to show the results of some of them. And this is work that was led by Qureshi in 2018 from UCLA. It's an undergraduate actually that led this work. And what they were looking at was how much fractional change in the period can you expect just by ingesting a Jupiter's mass worth of material, or smaller. So here we're seeing on the x-axis the mass of the companion, and on the y-axis we're seeing the fractional change in the spin period. And we're looking at it for stars or hosts of different masses. So we can do it for very low mass stars that are 0.8 solar masses, shown in green. We can do it for sun-like stars, which are shown in these blue curves. And we can do it for stars that are slightly more massive than the sun, these 1.2 solar mass stars that are shown in red. And the difference between the dashed and the solid line are when the ingestion event occurs, if it's happening at 100 million years or 600 million years. And that is very important for the dynamical models to consider. And you get some spread there in the parameter space. But what's important to take away is, let's look at just those y-axis values that are going between, obviously 0% at the very lowest, but all the way to 100%, where you are, you're changing the spin period in a significant way. And you can see if you just take a Jupiter's mass worth of material, which is shown there with the little Jupiter icon as to where that it would exist, for a 1 solar mass star to ingest a Jupiter's mass worth of material at 100 million years, you're talking about a 60% change in the spin period. This is non-negligible. This is observable changes in spin. And so the idea that those outliers could be created by this sort of event is founded in real simulation studies. It is true that this is one possible pathway, but we'll need evidence to really show that that was the progenitor system that created this anomalous rotation that we're observing today. And the takeaway from this plot is that if you want appreciable changes in spin, you favor having more massive companions, lower mass stellar hosts, and that's true for even really young clusters. So this is able to occur at 100 million years, 600 million years. There's a slight difference there depending on when it happens in terms of how appreciable it is, but it doesn't go into non-negligible terrain or anything like that when you look at those age differences. So that's pretty remarkable. But again, we're going to need some kind of smoking gun that can help us disambiguate the cause of the anomalous rotation. The rotation on its own is not a sufficient information for us to make any kind of conclusion about what created it. But chemistry is much more interesting in this way. Chemistry is easier to disentangle the progenitors. And so I became very interested in, let's find these rapid rotators in clusters, and let's take very, very high resolution spectroscopic analyses of them, and let's see what sort of chemical signatures they have. How are they different than a nominally rotating sample? And are there certain signatures that we would expect to find if they ate a planet? But what chemical enrichment signatures should we expect to find? I'm going to spend the next couple of slides talking about that. So in this plot, we are looking at abundance signatures. We use often these rocky chondrites as proxies for what the composition of a planet would be. And these chondrites basically have left over in our own solar system this pristine record of what the solar system was comprised of. We call it a meteoritic abundance. If you hear me say this word again, I just mean sort of the initial metallicity of an object is left over in the record of this chondrite. And that's because chondrites don't get very hot. They don't have central temperatures the way that a star would, or even a brown dwarf would, to appreciably change the chemistry that they were born with, which is wonderful. And we can compare that to the y-axis, which shows the abundances of our own sun's photosphere. And what we see is a nice one-to-one line there, where most things are, pretty much the same. Where if you look at the silicon, for example, in a chondrite, you're right there on a one-to-one with the solar photosphere. But there are some elements that are more abundant in chondrites than they are in solar photospheres, such as lithium. So lithium is shown there below that one-to-one line, where we tend to have 100 to 1,000 times more lithium per unit mass in a chondrite than in a host star. So this is very exciting. Another way to showcase this plot is if I just take the ratio per unit mass of the chondrite abundance to the solar abundance, we can see what is 100 times greater in chondrites than stars, and it's not a whole hell of a lot. Here I'm plotting elements all the way up to uranium, and just was looking through to try to figure out what would the smoking guns be. And lithium, which is shown there, is the third element that goes all the way to that 100 times mark, it's shown in maroon. That is one of the few. The next one that hits that same 100 times mark is tellurium, which is ridiculously difficult to observe in stars. And then iodine is the next contender, followed by there's cesium. And so you get a few other elements that are interesting to look at, but you're dropping off by a factor of 10 pretty quickly here. So lithium really is the first sort of smoking gun that you would want to look for. Where you would find rapid rotation, I would want to see evidence of lithium in order to determine anything about the progenitor pathway that ought to be there. But in what sort of statistical significance and what sort of abundance, how dilute is this signature? This is going to become important, and we're going to talk about this in a few slides. But first, I want to just talk about how do we even look at lithium. Lithium has a specific line around 6,708 angstroms. So here we're just looking at basically an absorption spectra in angstroms on the x-axis, so just looking at the wavelength versus the relative flux. We have the sun shown in red, and then we have a lithium-enriched G-type star that is also on the main sequence. So it's basically a solar analog that happens to be enriched in lithium. And what you see here is that it is an analog in all intents and purposes when we look at the iron lines or the calcium 1 line. But this lithium line at 6,708 angstroms, you should notice that the red spectra above is very minor. There's, it's almost a unobservable absorption feature there, to whereas the lithium enriched G-type star has this very strong absorption feature. And this is exactly what we look for in the spectra, is that particular lithium marker, which is easy to see in the optical when you have an object that is enriched in lithium. And people have looked at large populations. So there was a recent survey using LAMOST data where they looked at a whole host of objects. I don't know what their initial sample was, but of this sample, they found 10,535 lithium-enriched giant stars. These are objects that were more enriched in lithium than what you would expect from their, just from the decay process of lithium with time. This basically corresponded to 1% of their sample. So 1% of the G and K giants that they looked at were lithium enriched. Okay, it's 1%. Now we know what their initial N was. And of that sample, of that 10,535 lithium enriched giants, 6% of them are super rich. What I mean by that is, in this plot of the count of these lithium enriched giants to the strength of their lithium signature, which we're showing on the x-axis, and what is known as this 12-point scale that we don't have to get too much into. We're just basically comparing the number of atoms of lithium to hydrogen, and we're putting it in log space so that we have nice workable numbers that are not too large and not too small. But you see this meteoritic line at 3.3, we call it dex for units, at 3.3 dex. And what you should see is that there are objects that are rightward of that line. And that is weird, because it means that these are objects that have more lithium than what we would believe they should be born with if they had meteoritic-like abundances. That's quite peculiar. And it's even more peculiar when you consider the fact that this is a giant star, meaning it should have destroyed some of its lithium. It's a quite fragile element. It's not an element that's very easy to keep at these late stages. And so these are objects that we know are not merely preserving the lithium that they're born with, they're somehow becoming enriched in this chemical. And so that's another smoking gun, that something is at play here to cause this lithium enrichment. It's not something, it's not a preservation process. So that's quite interesting. So what we decided to do was to take a whole bunch of lithium abundance information from a survey known as GALA, and to map on an HR diagram, just taking hundreds of thousands of stars at various points in their stellar evolution, which we can trace as luminosity versus temperature. And we're going to see how that lithium changes as you move throughout that parameter space. And overplotted atop this, I have these stellar tracks. God, I really wish I had a way to annotate or use my cursor. I do not know. I'm just going to zoom out for a second, because I think it's actually pretty important to show this. So I apologize that we're sort of looking at not preview mode, we're looking at it in preview mode. But these stellar tracks are stellar evolutionary models that show you how a star evolves as a function of time. So here on this sort of plus sign here, what I have is the main sequence turnoff point. This is the point at which a sun-like star at 1 solar mass is running out of hydrogen in its core, and it's beginning to expand in size. Its luminosity is starting to increase as we reach this point here. It's expanding in size, and therefore its surface area is much larger. And this is showing up as a brightness increase, and that continues. And what we can do is we can see in these background hex bins what the associated lithium abundance would be for objects at these various points in their stellar evolutionary cycle. So this is wonderful. We also can figure out what's the variance. So in addition to getting a baseline, what's a typical median lithium abundance measurement for a star that's on the main sequence turnoff at 1 solar masses, we can also figure out what sort of standard deviation there is as well. So we can get statistical significance by having this data-driven approach, which I think is very useful. And what we focused on was sort of points between this main sequence turnoff and this triangular point here, which we're going to call the luminosity bump. And it has to do with a chemical discontinuity where things become a little bit confusing in terms of the chemistry of the star. It can start to self-pollute, and its photometric absorption, its photometric abundances start to change. So really between here and between here, we do not expect that to be happening. The star should just slowly be depleting its lithium, which we can see mapped out by the law survey data, and we can determine where there is an outlier in this sort of HR diagram space. Okay, let's see if I need to do anything else here. Okay, I'm going to go back into preview mode because I don't think or play mode. Okay, so what we did was we made these stellar models where we had a sense of how much mass the convective envelope, the sort of outer region of the star, I'm going to go back in, this outer region here would have. And we knew the temperature of that region. We knew information about the densities and pressures, as well as even the more interior radiative zone. And what we could add was, we could add in this supply of lithium from a planet, the supply of hydrogen from a planet, which we know pretty well from lots of studies like Montalban and Ravallo 2002, how many atoms about on average a Jupiter would be able to offer in terms of its lithium and hydrogen content. And we could ask ourselves, adding in that material into that convective zone, what sort of abundant signature would you get and how statistically significant was it? So where can we even have a hope in observing these sort of contamination signatures anywhere? And that is what I'm plotting here. So here I've overplotted in color the abundant signature that is resulting from consuming a Jupiter's worth of lithium and hydrogen, adding it into the convective envelope of the star. And I'm showing in color how that abundant signature changes depending on how much mass is in that outer convective envelope. As you might expect, as the star is evolving off of the main sequence and getting larger in size, that signature is going to be more and more dilute, right? How much the number of atoms of Jupiter's worth of material can supply is constant, but what's not constant here is how much mass basically that overall reservoir from the star entails, and that is increasing with time, and therefore it's not surprising that that signature, the strength of the signature, decreases as a function of time. It's hard for us to evaluate anything about statistical significance here because that's not what's being shown. What's being shown is the overall strength of the signature. But you may remember from this particular plot that meteoritic abundances were that 3.3 dex value. And one thing we can take away is that near that main sequence turnoff, when you're talking about a star that's 1.4, 1.6 solar masses, you're reaching these meteoritic abundance strengths. So this is already interesting that these are cases where you're not going to be able to just conserve your lithium supply. I'm going to take a moment to just say what these lines are because I hate to show things where I haven't talked about them. These lines are lines of constant radii. You can relate temperature and luminosity in equation to get these constant radii lines. And these lines basically pertain to the orbital separation of companions. So here we're seeing this edge to this edge is the hot Jupiter zone. So an object, a sun-like star at this particular point, the size of that star basically is large enough that it would extend into that inner boundary of the hot Jupiter zone. And then we have just some example planets with orbital separations atop this. So you can get a sense that at what point, for example, this system here is TRAPPIST 1b. You can figure out at what point each of these stars would intersect just because they're so large now in extent, they would completely engulf an object at the same orbital separation as TRAPPIST 1b. So you can kind of look in to see, get a sense of how your star is increasing in size and how that impacts the sorts of objects that you would engulf. Okay, but we don't have a sense of, again, the statistical significance. It's all well and good that we're super meteoritic, but what does that even mean in terms of being able to detect this? So that the next figure is much more illuminating, I think. So here we're showing overplot, it's the exact same plot, but now we have overplotted the statistical significance by taking that data-driven approach with the GALA data. And what we see is that 5 sigma statistical significance is possible, but it's not possible for a whole hell of a lot of systems, right? So for most of them, we're well below 1 sigma, but if you're near the main sequence turnoff and you're 1.4 to 1.6 solar masses, you're able to get a statistical significance that's pretty remarkable. So these are places that one would want to look. I'm going to take a moment, make sure that we're not too jargony. If anyone has any questions or wants me to clarify anything.
Can you define the unit of a dex?
So it's this silly equation that it corresponds to. First off, you'll see dex in all sorts of places. If I was talking about the metallicity of Fe over H, dex will pop up. If people are talking about ages in log space, text pops up. It usually means that whatever number we're talking about in this logarithmic space. And what that for me means is that the numbers obviously are just not sort of these human counting numbers. They're either very, very large or they're very, very small. And so we're putting things in logarithmic space generally, so we can sort of talk about either a wide range of numbers, or we can just talk about numbers that are so ridiculously large. So in this case, in this 12-point scale, which is what it's called, we're just taking the log of, take all the lithium atoms that a star has. Here we're having star plus planet because we've ingested something, but could be just the star. And we divide by the number of hydrogen atoms. And because on average, there are 10 to the 12 more hydrogen atoms than there are lithium, we're gonna add this number 12 to sort of get everything back to a 1. And that's what we do. So if you hear that number, it just means we're in log space, but it can mean lots of different kinds of measurements in that log space.
So does it short for decimal exponential or?
Yes.
Yes.
Okay.
Yeah, so
that was my long-winded decimal exponential.
Yeah, so a dex of if you go from 1 to 10, that's a dex of 1, but if you go to 100, that's a dex of 2. Melinda, I had a question. I was getting a little lost because we're talking about hot Jupiters here having the greatest impact, obviously, and that would be the most interesting to watch the impact on the host star. But at the same time, you're talking about the chemistry of chondrite composition in lithium, which would indicate, I would assume, rocky planets. So I'm trying to understand the connection between the hot Jupiters and the lithium and chondrite, because at least my understanding of our Jupiter is that most of the lithium is atmospheric, and it's not much more than it would be on Earth.
That's true, but we expect that these objects form via this pebble accretion method. And so you get these cores of these objects that have to be massive enough to start accreting these gaseous envelopes to create what we then see as being this gas giant. But really, the chondrite abundances, the brown dwarf abundances, the exoplanet abundances are not all that different from each other, because they all form from a common molecular cloud that makes up the solar system. So the outer atmospheres, you're absolutely right, are drastically different in terms of what we're talking about, or what James Webb would detect as abundant signatures. But when you start to go sort of deep to the object, that's, to the properties that are making up the bulk mass of the object, it's not all that distinctly different anymore from what we believe. Okay. But there are problems.
Because the outer atmospheres of these really expanding gaseous planets tend to evaporate and be blown off before they really get finally absorbed.
Oh, that's a whole other aside that I don't even take into account at all in our models. So we're not accounting for any kind of tidal heating or any kind of ablation. We assume that if you just were to deposit everything, let's say it's ablated, but then it gravitationally rains back on later, we're not going to make any assumptions. Let's, in the most optimistic of cases, just liberate all of the material, assuming that a gas giant can be basically scaled up from a rocky chondrite, thinking about its internal composition, rain all that material in, and then try to see, are there areas in this parameter space where you would not expect, even in the most optimistic of cases, to get any statistical significance. You can rule these guys out right out the gate. So if I saw lithium enrichment in a solar mass star, a sun-like star, at some early phase of the red giant branch, you're either eating multiple hot Jupiters, and we actually have a plot in our paper where we see how many Jupiters worth of material. Do you need 10? Do you need 50 of them? And it starts to get so unreasonable that this is not a likely pathway. And so you expect there to be some other contamination process. But in this most optimistic of case, are there places where there's still some interesting hope of looking for them? And that's what we're revealing here. But it is very much a toy model that doesn't account for what can be lost from the system forever in terms of that outer atmosphere. It doesn't account for the fact that, is the lithium homogeneously distributed throughout? Is it a lot of it locked up in the outer parts of the crust? I mean, there's none of that is being considered at all. We're just disassociating everything, depositing it in. And the truth of the matter is that, talking to geophysicists and planetary scientists and trying to get a sense of what are the answers to these questions, there's a lot of unknowns. And so being in toy model terrain is probably the most honest place to be, because there are still so many unknowns.
You've got to start somewhere. Thank you.
You gotta start somewhere.
Yeah.
Yeah.
And Melinda, one of the things that was, this isn't probably a stupid question, but I'll ask it anyway. I'm fearless on that. When a star absorbs the mass of one or two hot Jupiters that might be orbiting it, wouldn't that affect the mass of the star itself? And could that actually arrest or delay the expansion of that star because of the additional mass?
It's a good question. The mass deposition is pretty, it depends on how you want to consider what you want to consider negligible. So, if it's 1,000 times different, so it's not going to be an overwhelmingly discernible amount of mass to appreciably change, some of the observational properties outside of like abundance and rotation there. However, what you're saying is something I'm actually studying a little bit with a professor at UCLA. We're thinking about could there be changes in the mean molecular weight or the opacity because you're accreting material that is very dissimilar chemically. And can that invoke changes in the luminosity and the temperature? Can we see that on a CMD diagram? And if so, what sort of conditions do you need for that to be true? What if it's wildly lower in metallicity, for instance, or wildly higher in helium? What are the sort of observational effects then? So you can play a little bit of those games. So I think it does become important to think about what we're doing to the host star in terms of its observational properties. But I haven't thought too much about the mass in and of itself outside of how it affects the luminosity and the temperature. I'd have to think more about that too.
Yeah. Okay, thanks.
Yeah. Yeah, and I know everyone says it and it's cliche, but there really are, if you have somebody who just genuinely is interested in stuff, I think there really are no stupid questions. It's always just like a portal to like another way to think about something or a way to clarify something. So I genuinely mean that. So I appreciate it.
Melinda, can I ask you a question?
Yes, please.
Oh, good. Since lithium is such an important element for making these new batteries, we find that lithium is not very well distributed among the crust of the Earth. I mean, there are pockets of it, which makes it very interesting geopolitical problem, And so I was thinking when the comet, I think it was called Shoemaker, wasn't it? When it entered the penetrated Jupiter, I don't know, probably more than 10 years ago already by now. Did we have any evidence of a profile of lithium as the comet particles or objects went into the Jupiter atmosphere?
That's a great, I would imagine so, but I don't know. I don't know with Shoemaker-Levy. I never looked at those if there were any abundance analysis. I would imagine that it would be a travesty if that wasn't done. But we can do one better, which is that these chondrites fall to Earth and we can break them open and we can see the lithium content, which is how we get these very measurements, is you actually are able to see these objects that are falling from space and you can actually pick them up and measure them. And as an astronomer who so rarely gets to have anything to pick, it's remarkable. There are issues though. Issue one is that we're assuming, there's some good reason to assume it based on the spectral properties, but we are assuming that chondrites are these analogs of larger rocky bodies and analogs of cores of these giants. But an even bigger problem that I think that we're going to have to figure out how to get around, and I have a couple ideas as to how, if we want to talk about this, is we're taking these solar system bodies and then we're extrapolating them to these exosolar systems, right? And that is hugely problematic. The issue is that this is a constraint that we just have. This is where we happen to live. These are the chondrites we happen to see. And here we are trying to extrapolate, but we know that there are wild divergences in all sorts of ways when it comes to exoplanet from our own solar system. And, we know that stars come in all sorts of metallicities, right? So this is also a situation that we have to account for. One way I think that we can get around this, I won't go into it too deeply unless there's more questions, but is we see white dwarfs that are polluted with rocky bodies that are falling onto them. White dwarfs have really short, they're very high surface gravities, very compact objects, meaning that heavy elements sink really quickly, and you really should only see hydrogen and helium in the outer confines. So any sign of lithium, beryllium has been observed, cesium has been observed, is an indication that some rocky material is actually actively accreting onto these objects. And in fact, 50% of these white dwarfs are shown, 30 to 50%, depending on who you ask, to have accretion signatures. And so I think that we can get nice constraints on the systems of different open clusters, for example, on the type of chondrites you'd expect therein by looking at their white dwarf population, and the white dwarf accretion signatures, I think, can tell us how much diversity there is cluster to cluster in the rocky bodies material. So that's one way around. But yeah, sorry, I went on a tangent there. But yeah, lithium's a real problem on the Earth, and I just listened to a talk recently all about mining asteroids and how much mining asteroids are going to really change the game, and that we'll see the world's first trillionaires. And yeah, I'm sure some of you are familiar with this idea, but yeah, there's a couple asteroids that have been identified in particular that are just worth a ridiculous amount of money. And at the moment, the technology does exist to go out and to mine these things, but financially, there's not enough of a profit to really compel people to do it yet. But that this is something that I know Thomas Zurbuchen, who's one of the leads at NASA, thinks is inevitable and is going to come. And there's no legislation either. So this is a free-for-all Western world of getting rich off asteroid mining that we're going to have to figure out as we go, how we regulate some of these things and how we do not contaminate low Earth orbit and all of that. So space policy is going to need to get fixed, I think. Okay, I'm going to go on to the next slide. So cool, we have the idea that in sort of an optimal situation where we liberate all of the material, we throw it all into the convective regions, we can get statistical significance. However, I would not encourage graduate students or anyone else to spend a whole hell of a lot of time looking for these things if they're really short-lived, right? It's no good if we get a 5 sigma detection, but it's swimming in there for a week before it's destroyed. So we really wanted to get a sense of the timescales. How long can we expect these objects to be polluted? And luckily, because we had this data from Galah, we can actually see the time, basically the time steps as these stars, just left to their own devices, are depleting their own lithium reserve. So we have a sense of what the lithium destruction conditions and timescales are in stars. That is data driven. And so as much as I love theory, I mean, I think that, theory has to be sort of constrained by these pillars of data that are able to sort of make sure we're not going into an interesting logical terrain that has no bearing on physical reality. And so this is why I really appreciate some of these large scale surveys, which can tell us these timescales, because there are a lot of theoretical calculations that I can also run that can give them. And we did do that before turning to Galah data. They didn't disagree all that much. It was less than an order of magnitude, even in the worst of cases. But, I still think that we want to be as data driven as possible. And so looking at these, statistical significances, we can say, well, how long is that going to stick around? And not only how long is that going to stick around because of the destruction or depletion mechanisms therein, but the fact that the star is evolving. And the later the star moves along its evolutionary track, the quicker those time steps go. So it's spending a whole hell of a lot of time right here on that main sequence turnoff point, right? It spent most of its life just sitting on the main sequence, 90% of it or so. But these time steps just get smaller and smaller and smaller as you move along, because it's just basically becoming more and more frantic, if you think about it that way, to overcome gravity as it's burning through its energy reserves, its nuclear energy reserves. And so we played the game of, let's zoom in on that region that we find to be of interest, where we see the statistical significance, and let's ask ourselves, how long will the signatures stick around? And that's the plot shown here, where we're looking at log of time, but let's go ahead and just pair next to it a nice table, which is how I prefer to look at information. And breaking down that 1.4 to 1.6 region where I said was most interesting in terms of the statistical significance, we could see that the lithium survival time is pretty long. We're looking at half a billion years for a 1.6 solar mass star, nearly a billion years for a 1.4 solar mass star. That's how long it takes to basically burn through all of the lithium that was added to the star. It's not how long it's going to be 5 sigma, but how long it's going to take to remove all of it. But what it means is that that signature is a long-standing one, and one that is worth looking for. But why do we care? Why care at all? It's sort of an exciting, topic, this idea of stars eating their planets. But what does it really mean? And what I really would like to drive home here is that while JWST and other transmission spectroscopic instruments will tell us things about the outer atmospheres, these thin outer atmospheres in many cases that are surrounding these exoplanets, they tell us very little about bulk composition. And really the only 2 ways that we know of at the moment as an astronomical community to measure bulk composition, I guess 3 ways. If you have an object falling onto the Earth, you can measure the bulk composition of the chondrite. That would be one. So one way, you're going to be out of luck when it comes to anything much larger than that, however. And another way is that white dwarf accretion process, where we can just measure what looks peculiar in a white dwarf's atmosphere when you wouldn't expect there to be anything but hydrogen and helium to be observed. And the third is this ingestion process, where you have an object that is ingested in that outer envelope of the star. You measure that star's abundance, and you see in what ways it is dissimilar from stars that are like that similar in mass and similar in evolutionary state. It's even one better if you can find stars that are in these open clusters, because open clusters share metallicities. They're well constrained. They share ages, they share distances, they all form from one molecular cloud. They're gravitationally bound in some cases, with the open clusters less or so. But these are objects that basically should be, siblings of one another. And so these outliers, both in rotational space, which I showed earlier in that rotational curve, but also in chemistry space, are easy to stick out. And so you can learn things about not just the signatures I expect, like I wouldn't just be able to see the lithium absorption signature that I'm looking for. I might be able to compare a nominal sample of cluster stars to an enriched, rapidly rotating star and see in what other ways, what absorption signatures did we not even think to look for that show up to be statistically more enriched or less enriched in this particular type of object. And so that's something that we're hoping to do. And we're doing this by looking at a whole heck of a lot of clusters. And there are lots of them. I'm sure they're a wonderful thing to observe. So as astronomers that actually look up at the night sky, they're probably near and dear to your hearts as well, which is amazing because they are pretty breathtaking. There are globular clusters and open clusters, which I'm sure all of you know, like the back of your hand here. I tend to focus more on open clusters because they're closer by, they're younger. There's a sort of wider range of masses that can be accounted for. The angular separation, because they're closer by between stars themselves, is a little bit greater in many cases. And so the blending is less of a problem. And so that tends to be my favorite place. And basically, if you have stars that are forming from a common molecular cloud at T=1 or T=0, when they're on the 0H main sequence, they form this, again, this luminosity versus temperature main sequence diagonal line here. And as time goes on, we're seeing sort of 3 different objects on this particular plot. This is going to be the 2.6 solar mass star. Here it is on its main sequence being much larger than a 1.0 solar mass star, which is there. Here we have a 0.7 solar mass star. Some differences about the internal properties. This is because these have outer convection zones. It has to do with how energy is being transported. This has a radiative zone. But we can start a simulation and we can look and see what happens as a function of time. Ooh, and it goes fast. So we're going to go through it and then I'm going to explain what's going on. What's happening is stars are peeling off of the main sequence as time goes on. Stars that are more massive are running out of their core hydrogen supply. They're expanding in size. I'm actually going to drag it through. So right now we're looking at the 3 and 2.8 solar mass stars turning off the main sequence, which is literally why we call it a main sequence turnoff. They're, if you look and see on the right-hand side, expanding in size. They're getting more luminous. They're getting cooler because they're getting larger as well. So their effective temperatures are going down. And these objects are now being shown as red giants on this giant branch. And after time goes on, they start to become white dwarfs and cool. So you'll see in that left-hand corner, slowly these objects are becoming populated. So the older a cluster is, the lower mass, the most massive star it has is going to be, because basically there's been enough time for all its more massive objects to evolve off of the main sequence and to start inhabit this white dwarf terrain and this red giant terrain. So this is meant to tell you that if I look at a cluster and I see where its stars are in visual magnitude versus B minus B or any kind of color magnitude space, we can age date it just based upon the location of that turnoff, because we just know how stars work. You know, if there's a companion or some differences in metallicity, you can start to talk about how things can go in slightly different ways in terms of these evolutionary processes. But by and large, for isolated standard stellar evolutionary models, it's like a clock that you can get a sense of what the ages of these objects are. And so we can look for objects that specifically have stars at that 1.4 to 1.6 solar mass turnoff, where we would expect ingestion to start occurring. They're expanding. Some of them are engulfing rocky bodies. Those rocky bodies, if they are completely engulfed, are going to contaminate those outer photospheres, those outer convective envelopes. Those outer convective envelopes should be able to have appreciable lithium signatures that they're statistically significant and they're long-lived. And so that is exactly what we're doing and how we're looking. And we're looking with Gaia data, Kepler data predominantly. We do pair it with Gaia, but it's predominantly this Kepler photometry. And we've been looking in several different fields, but more recently, we're looking at NGC 6819 and NGC 6791. This particular cluster is my favorite because the turnoff is right there, 1.6 solar masses, exactly where I want it to be. And we're looking for the rapid rotators, and we want to follow up with spectroscopic surveys to see, do they have enhanced lithium, and what other ways are they weird? What other chemical signatures are the smoking guns that something like that might have happened? And here in Wisconsin, we have access to lots of data from what is known as the Win Open Cluster Survey. This is 20 years of really precarious, painstaking radial velocity information that tells me whether or not objects are in a binary. It gives me a sense of cluster membership because they should share common radial velocities as well, so I can disentangle what is a field star from what is an actual cluster member. And I can combine all of that information with sometimes test data if I have test information as well. So that gives me real high frequency sort of photometric sampling. And at the moment, I have students that are working through classifying. This is all just meant to show you that we have lots of light curves and they create lots of patterns, and some of them are indicative of pulsators and some of them are indicative of eclipsing binaries. But students look by eye at every single star, tens of thousands of stars, and work to classify them based upon everything we know about them. Their membership probabilities, whether or not the radial velocity information indicates they have a binary, whether or not the light curve is shaped in a way that would be indicative of there being a transit event or there being pulsational signatures. We map all of this information into a color magnitude diagram, fitting it with these stellar tracks to get a sense of the age and the turnoff masses and the spectral properties. And this is a graduate student who's talking next week here at your Madison Astronomical Society. We worked together last year. She did a lot of the membership analysis using proper motion information. And we are then going in and we're looking for the rapid rotators and looking for the pulsators. And there's all sorts of science that inevitably accompanies this sort of, careful analysis. So there's many projects that we're sort of putting a pin in as we go to try to just get out a strong catalog and find our rapid rotators. And then there's an undergraduate here at UW-Madison, Rihanna Kenzie, who's been doing a lot of the rotational analysis. So here I'm showing you in the same CMD of the same cluster, in red are our rapid rotators. These are objects with periods that are below 15 days. There are a ton of them, so this is exciting. This is great spectral follow-up for us to go in and look for lithium. And I'm going to go ahead and summarize and just open up to conversation or however you want to spend the rest of this meeting. But number one is that we have a lot to learn about stellar hosts that are not on the main sequence because our census demographics right now are pretty heavily biased. That's great because we've learned a ton about sun-like stars and middle-aged stars with planets. And it really has expanded our own understanding of what the flavors that exoplanets can come in and the orbital architectures, which sometimes wildly depart from what we see in our own solar system. Number two, that studying stars off of the main sequence will offer constraints and insights to both stellar astrophysical communities, because it can tell you why stars are behaving the way they are, if they're rapidly rotating, if they're chemically weird, if they have these strong infrared excess that's indicative of ejecta around it. You learn why this could possibly be the case. So stellar astronomers who don't normally care a whole hell of a lot about the exoplanet stuff really should care about the fact that it's not just stars that impact planets, planets can impact stars. And on the exoplanet side of things, we can learn things about bulk composition, and we can learn about how those bulk compositional properties may vary from exoplanetary solar system to solar system. So that's quite exciting. And lastly, that these rotational anomalies, these infrared excess anomalies, these possible photometric signatures, and most certainly the chemical signatures, it looks like for many of them theoretically are possible. For some, we see, most definitely evidence that this is happening, and I think it's worth looking for. And so this is something that I'm going to spend the next 3 years trying to get a handle on. And with that, just want to shout out to a lot of the collaborators and co-authors that made all this work possible. This is in no way the Melinda show. This is a lot of people that have painstaking work to make all these things possible. And with that, happy to answer questions or just have a conversation. So thank you so much.
Thank you, Melinda. Yes, let's open the floor up to some questions.
Lithium, Melinda, since lithium has two isotopes that are predominant, which is, I think lithium 7 is 92% and 6 is 8. If you saw those lines in that ratio, that would also be a proof that you're looking at lithium. Would that help?
That's true. There's some issues. Lithium 6 and lithium 7.
You might not have enough abundance, of course, statistically.
And there's other ways to make lithium 6. So there's something known as cosmic ray spallation. It's this idea that cosmic rays are literally raining down on the surfaces of stars, if you want to call it surfaces of the atmospheres of stars, and interacting. And so lithium 6 that was one of the isotopes I wanted to look at. In particular, I really focused on lithium 7. So all this analysis where I'm talking about lithium 7 or lithium in general is all pertaining to lithium 7, which you're right, is far more abundant than lithium 6. So I think for all intents and purposes, it's fine. But issue one is that there's other ways to contaminate lithium 6 that I would have trouble disentangling. Issue 2 is that it's far less abundant. So you're working with more dilute signatures if you're focusing on that as isotope. Issue 3 is that unless you have the spectral resolution to separate the lithium 6 from the lithium 7 line, which are pretty close together, I think it's like 0.1 angstrom. So, it's not impossible. It's something you definitely can do with the right instruments. But for many surveys, they get blended together in a common line where predominantly lithium 7 is driving the absorption.
Thank you.
Melinda, going back to the Jovian model, the hot Jupiter models, are all of the calculations you're doing based on hot Jupiter planets?
So it's just based upon, it's just the mass composition and the breakdown in terms of meteoritic abundance. We do scale it up. So we say, when we play the game of how many Jupiters would you have to eat, I think I can even pull up this plot. So we asked the question, okay, it seems like a lot of parameter space gets ruled out. Well, how many Jupiters do you need to eat to get a 5 sigma statistical significance? That's another game you can play. And so we can just assume here that a 2 Jupiter mass object has twice the amount of lithium. So again, a toy model that we're just sort of extrapolating and scaling. So this is something that we did there. But it's pretty simple in terms of what's being considered. We're not really considering anything about the initial orbital architecture, whether it started off as a hot Jupiter or was kicked in violently via some dynamical process. The game we play is somehow the planet gets into the star one way or another, either dynamically or slowly merging with time. We won't worry about the angular momentum transfer, the energy impart, none of that. Let's just take the chemistry and sprinkle it through the convective layer, all of it. and let's see how dilute that signature is then. And we can scale it up and down and play this game. And you can see there's like an empty region here in this plot where you really would need to get beyond what even a brown dwarf would be able to provide. We go all the way to 63 Jupiter masses, and anything above like 13 Jupiter masses, you're already in brown dwarf terrain. So here you're having to get multiple brown dwarfs rained on. We're like, this is getting fantastical, forget about it. But you can see there are other regions like, this 1.8 solar mass star, this 2 solar mass star, where you're still, just slightly above a Jupiter's mass, and you're now in interesting territory. But really, that's the only sort of constraints that we play, is just how much lithium do you expect a gas giant to have, just scaling up from a chondrite. And let's sort of scale that if we want to talk about an even more massive object. So there's certainly a lot of improvement to be made, but not without a whole hell of a lot of guesswork, and I'm sort of weary to constrain it any further until we know more. So yeah. I'd much rather sort of rule out regions where, like, let's not look here, let's continue to look here, and now that we know we have this evidence, let's go in and look at the chemistry really carefully with a resolution of 100,000, and let's compare it to things that have no sign of engulfment process having had occurred at all. And now let's start to disentangle things about the bulk composition of these objects.
Yeah, I guess the point I was making is that our solar system being atypical, not having hot Jupiters, would actually be uninteresting to you from a study standpoint, right?
Unless, I guess the question I would have to ask is, if we know that the atmospheres of the Jupiters, okay, if we assumed that the atmospheres of these Jupiters is not where the lithium is locked up, but the lithium is actually locked up much deeper in the star, and we know the core mass is not that different than the mass of a rocky body, maybe it's the same game all over again. But I think we need to get clear about that as a community before I would be sure. Where is the lithium locked up is the problem, and is it distributed homogeneously? We see, for example, with white dwarf accretion processes, that there are these sort of episodes or chapters where certain volatile species that are easier to liberate, this is often happening through like ablation and photo evaporation and stuff as well, but you see there's sort of like different chapters of what's raining down. And so this idea that even if it's not isotropically distributed, is it even being disassociated at the same time? Probably not, right? Because these are these different chemical, there's just different energies that are associated with actually unbinding those chemicals. And so I think, that's a little bit tricky, but I don't know that the rocky situation will be that different if the lithium is deposited outside of the atmosphere predominantly.
Right, okay.
Yeah, do we have any more questions for Melinda?
I do. What's a chondrite?
Great question. So I think chondrite and meteorite are used pretty interchangeably in most cases. So really, it's a meteorite that's not been modified by any kind of differentiation process, any kind of melting from the parent body. It hasn't been heated up into extreme conditions because it went really close to the sun. It's an object that is thought to be pristine, small little rocky object, not nearly even close to like Earth-sized or even much of a substellar companion in any sort of way. I can get a sense of how, like, what the size spread is in them. I'm not sure. I've seen some that are like the size of my palm, but these are objects that are thought to have abundances that are indicative of what the very early solar system would have had.
Thank you.
Yeah, let me see, chondrite sizes. They're generally about 1 millimeter in diameter. So that, very large in the case of your palm, but.
Melinda, I had a quick question about slide 30. If you go back to the distribution there on slide 30, it looked to me like it was a really smooth distribution, and I don't see anything special about the stuff that is above 6% there.
No, totally beautiful. But I guess what is the first situation is that when lithium enriched stars were found, they were generally found, they're largely about 1.5 dex, okay? That 1.5
Okay.
dex is actually not that different than what a sun-like star on the main sequence would have. Our own sun is actually a little bit more depleted. It's like 1.05 dex, but regardless, 1.5 is not all that weird if you're on the main sequence. It gets much weirder because these are giants, meaning that they have a lot more mass that gets added to their convective envelope, that lithium gets diluted. And so really here you're already talking about weird terrain. But everyone expected that what you would see if you had enrichment at all is you get some kind of Gaussian distribution. But if that object was enriched because it was preserving the lithium it was born with, for some reason, it was not being depleted in a way that you would expect on the giant branch, you would not expect this tail to extend far out beyond 3.3 dex, right? This would be already kind of weird. Your point is well taken that it is a smooth distribution, meaning whatever is enriching these systems seems to be one process, one Gaussian process that applies across the board. My only point here in pointing out the meteoritic abundance is that there are pundits sometimes saying, yeah, how do you know that the star isn't just keeping what it was originally born with? And I think the existence of this tail is one way that we know that that is bizarre. It makes even less sense when you start to think about some of these objects are pretty well evolved. And so that 1.5 value is, already becoming far too generous. Yeah, but if it's all coming from a similar process, I think you're right that you would expect that to be a pretty smooth distribution.
Yeah, it looks smooth, but I'm not the professional astronomer.
That being said, there are other lithium enrichment processes that I did not go into. There are ways stars can self-enrich, and it seems to be a very common process at late stages in the red giant branch. So there are certain points in an HR diagram, there's something called a red clump, where we see enrichment really sort of starts to become much more prevalent. And so there are these processes where the star, which is creating helium from hydrogen via this thing called the PP chain. It's a process of how you basically are combining elements in all of the different nuclear networks that are at work. You can create beryllium as a byproduct of that. It's one part of the PP chain. And beryllium, I think it's beryllium 7, can decay into lithium 7 if you can circulate it up to regions in the star that are cool enough that the lithium can survive. So you need to be able to take the beryllium from deep down where it's hot enough to make beryllium in the first place, so the PP chain's active. And then it has a 56-day decay timescale, and you need to really quickly convectively bring that material up. And that is possible to do at these very late times on the red giant branch. And that's a whole other mechanism, which is why I really focused between that luminosity bump and that main sequence turn off, because then we can kind of avoid having to worry too much about those more fantastical enrichment processes being at play.
Mm-hmm, mm-hmm. I thought your talk was going to focus on nickel and iron signatures, but it looks like they're not, you just can't see nickel and iron. Is that why? I
mean, iron enrichment is definitely observed as well. And then there's all of these, refractory element studies that are being done now as well. If you see refractory elements, so that's another possibility. It's just hard, that per unit mass chondrite abundance plot really pops out to me, that if you want to be able to, especially if you're talking about later stages where you're getting more and more mass in that convective region, you're going to need something that really is quite abundant for a substellar object and not very abundant for a star. And those elements are objects that are just fragile to extreme temperatures, the kinds of temperatures that stellar cores can achieve, but a brown dwarf or a planet would not have any hope of achieving. So, lithium 7, beryllium is another big one. There's a lot of interest in cesium too, but it's true that another way to look at it is to look at ratios of, let's include iron, let's look at ratios with refractory elements. And those are other ways to possibly provide more evidence.
Melinda, I was interrupted a couple of times. You may have answered this question already, but I'm curious, how long does it take a star, one of your stars, to frankly eat up and digest a super Jupiter?
So the long and honest answer to this question really depends on the tidal forces that are at play, because as the star is expanding and that convective envelope is becoming deeper, and you have this more distant planetary body, there are real tidal forces that are at play that can perturb the orbit of that object so that you can ingest it quite a bit faster. Let's leave all of those technicalities inside and just think about, once the planet has basically intersected the outer envelope of the star, how long is it now taking to sort of completely disassociate and be done with your life as a planet? Oh gosh, this is the problem with asking a scientist any questions, because it's just like, oh, but then there's another complexity. It's a few integer orbits is the hand wavy answer.
I'm hearing a lot of footnotes right now.
And astronomy journals hate footnotes, and I love them. I'm constantly being told that, like, get your footnotes out of here. Anyway, it's a few integer orbits. And so these orbital timescales are very short. So you're talking about this happening now, weeks is what you're doing to actually unbind this object. It depends though, however, when is this happening? If it's happening when the star is completely extended, to 200 times its size, now you're talking about an Earth that has a 1 year long period, for example, that you could be disassociating, and a few integer orbits of that is now going to be a few years, right? So it really depends, when does this happen? It also depends on whether or not you actually can dissociate the thing. And I didn't get into the weeds of, are you actually liberating all of the material? I mean, how much gravitational unbinding do you really expect? If you have a very dense, for example, you have a brown dwarf that is 100 times denser than a red giant star, do you really expect that lower density environment to do a whole lot of damage in unbinding all of that material? And so we've actually looked at this quite a bit. And what we've seen is that in some cases, if you have massive objects, they can survive the whole damn experience. And so what you end up with at the end of that is a white dwarf with a charred planetary body that's orbiting it, that is probably now raining down material on it. But that's really only for the cases where you have appropriate densities. And so there are some situations where you don't expect to liberate all of the lithium that an object would have. And so hot Jupiters are a safe place to be. Jupiter mass seems like unbinding is a possibility. But when you start talking 13 Jupiter masses, 10 Jupiter masses, depending on which calculation you use and what sort of assumptions you're making, you're getting into a terrain where it may be possible to survive all the way down to the radiative zone and orbit a white dwarf at some time stamp later. And we see those objects, we see close orbiting objects around white dwarfs. And the question is, did they survive engulfment? Did they slowly orbitally migrate over there at late times as the star is losing a whole bunch of material and perturbing the objects that are in orbit around it? Is there even a second stage of planetary formation as it ejects a whole bunch of material? That material falls back in orbit around the white dwarf, and can you actually start to coalesce and form planets at these very late stages? Perhaps. So those are sort of three possible channels that might explain these objects that we see pretty frequently, that are around, often in debris disks and things like that, already disrupted, but close enough that it doesn't make sense that they should have been there all along. I don't know, maybe Bob Aloisi has something to add there. Not to put you on the spot, Bob, but you're the white dwarf person. But this is not uncommon, right? These debris disks around white dwarfs. And
no, and we're finding more and more rocky, dusty bodies, which are actually breaking up as we watch them, and then they're going to eventually end up on the surface of the white dwarf.
There's a beautiful paper that's actually a very fun read. I know scientists lie when they tell you something's a fun read, but Dimitri Veras, V-E-R-A-S, is a phenomenal writer. And he writes review articles, which tend to be, I think, a lot more user-friendly. I'm going to just show an example of what I'm talking about here. He talks about like post-main sequence planetary evolution and gives you all sorts of, what different effects are important to consider versus on the planetary system that you have in mind. And what I want to show you, the actual thing I would like to show you, is this particular chart. I wish I remembered what number it was off the top of my head. Oh, you know what? It's in the newer one. Forget it. He has a plot that basically shows you the elements and the year of discovery. And what I would have shown you is that lithium was just observed being accreted by a white dwarf in 2021 for the first time. Beryllium was shortly accompanied that same discovery, was also found. So I feel like that we're sort of slowly populating across the whole periodic table, and it's a pretty recent boom in discovery space here, where they're looking at white dwarfs very carefully and seeing all sorts of contamination signatures. So I think that whole realm is, the next decade, I think, is going to really open up with that.
Yeah, I was thinking that I was hoping that Jürgen's question was going to lead to an understanding, are these events actually observable on a time scale that we can actually see them, or are they just theoretical? They're going to happen over millennia, or when you said that some of these planets are absorbed in a week, then that's obviously observable if you're from an event.
It is, but for looking for them, the situation is the occurrence rates. So if there's many of them happening and they're lasting for a week, you're in better terrain than if they are very rare. Like the supernova event, right, also has this long-standing signature that one can observe, but you have to be pretty long-standing in terms of one could go out and observe, infrared excess or something over the scales of months, weeks. But if you're talking about being thousands of years away, you're going to be sheer out of luck. And unfortunately, supernovae are not all that common. I think there's 1 per century in the galaxy. So you have to be sort of lucky in terms of where you look. And unfortunately, the occurrence rates for these guys are also pretty low. I'm looking for the exact number. I think it's 0.1 to 0.01 per. Yes, it is 0.1 to 1 per year in the galaxy. So unfortunately, not super common, which is why the idea that seeing a luminosity spike, it would be hard to go out and photometrically in a random way look for it. Fortunately, however, we see planets where the period of orbit is decaying before our eyes. We can literally observe from one year to the next, and we see a change in the period. WASP 12b is one system where we have measured an orbital decay, and we can actually, predict what that decay time overall will be for ingestion. And so there are now sites where we're sort of flagging. This is unfortunately not human lifetime in many cases, right? In all cases that I know of so far. But we at least are starting to flag systems, if we think for our species anyway, that these are the places to keep your eye on. And at some point, if we don't destroy ourselves, we will be able to observe such an event happening. I try to be more hopeful, but lately it's been very bad. So we'll make it, right?
What effect is James Webb going to have on this research?
Good question. Maybe, Bob, what does James Webb have to say for the white dwarf terrain? For me, very little, because for these stellar compositions and transit spectroscopy, I really don't get much about any kind of bulk information out of that. It's really not going to help me with abundances of a main sequence star or a early red giant star. But I imagine for the white dwarf game, this is really important in terms of figuring out what's raining.
For the planet that Andrew Vanderberg discovered, he now has an approved James Webb proposal to go back and study the atmosphere of that planet. So for exoplanet research, it's very exciting. We're going to start to understand a lot more about exoplanets. I'm not sure about bulk compositions. I think infrared studies and the kind of spectroscopic studies that Melinda's talking about are probably going to be the way we're going to learn more.
The NUID, which is on the WIND telescope, is what I'm most keen to use, which has like a resolution of 100,000. So that's phenomenal. But for habitability, when you're just interested in like what worlds are out there and do those worlds have signs of, ecological systems? Could there be any life? I mean, James Webb is the instrument that you want to answer those questions. Unfortunately, I think I won't go into this weeds too much, but it's much more ambiguous than people want you to believe sometimes, these signs of life, like how you disentangle whether or not there's real liquid water, or you just have hydrolysis that's taking place and it's not indicative of really much more going on other than there was an OH molecule. This is problematic, and I think sometimes we're being oversold, but we can at least start to flag potential systems that are interesting, and that is the right way to do it. And I think we're going to have to think about ratios of various species before we can get any kind of real habitability disambiguity, but that's a little ways away. And don't even get me started about, like, okay, you have an atmosphere, but do you have plate tectonics, and do you have magnetic field, and like what does habitable even mean, right? And how much does this have to sort of be replicated for Earth-like conditions? Do you need a Jupiter further out to protect you from all sorts of impacts? Like, there's going to be just added to this Drake equation as we go on, and as it should be. So the Earth is special, and we have no plan B, and we cannot escape to Mars unless we're very wealthy. And so we really gotta do better.
Or if somebody magically invents a warp drive to allow us to get to Mars quick enough.
Sure.
Yeah. Yeah, but then you still have to deal with the fact it doesn't have the magnetic fields you have on Earth.
Right. Yeah, a while back we had a very interesting presentation from a UW researcher that was working on how do you grow vegetables in space, because in order to get to Mars in the period of time where we can get there with the technology we have, you're going to have some way to grow food as you go, and they really didn't have any consoling answers or any confidence building answers to that yet.
We always have Matt Damon's potatoes to fall back on.
Well, thank you so much, Melinda. This is a really fun topic to think about. And I think the next time I'm pointing my telescope and showing at an outreach party a teenager or a child an open cluster, I can tell them a little bit of story of the kind of research that's going on right now with open clusters. So yeah,
awesome.
Thank you. So thank you so much for sharing your research. This is really fascinating stuff, especially for us chemists.
Very, very interesting.
Maybe I can pick your brain one day. I would say offline, but I guess online in a different way. I'm very interested in tellurium and why it's so difficult to observe tellurium, and molecular signatures, whether or not we can use deuterium in like an OD or an HD. And so maybe your chemistry expertise will be really helpful, because I'm in new terrain there.
Yeah,
we'll get Martin Mika involved in that one too.
Yeah,
He's not here tonight.
There's also interesting bits of astronomy is like the boron ratio, mass 10 and mass 11 is different on the moon than on Earth. So those are very interesting things, how that all occurred. For me anyways, I mean, I'm a chemist. I find it very fascinating.
It makes me hopeful too that we can say things about the actual bodies, right? Let's see, we see something being rained down on a white dwarf. Maybe we can look at these isotopes and not just say whether or not something substellar happened, but is it moon-like? Is it Mercury-like? And that will be really cool.
Yeah. Well, we also know when the comet hit the Earth, I think they estimate about 60 million years ago. There's I think it's an iridium layer that they have all around the surface of the Earth, which they can measure.
What? Oh, wow.
I think it's iridium.
Yeah, it's
one of those.
That's how they
decided
it was a
I have a lot of spurious information in my brain. But I find that's fascinating, that it's different than on Earth, Iridium was that's a very interesting element, by the way. It's very stable and it's very dense. I think its specific gravity is like 23. I think it's the most dense.
Wow.
Yeah, anyways, there's so much to learn, isn't there?
Yeah, no, it's great. I just feel like our life. So this is the other thing that I will not go too far into, but the human lifespan's not long enough. So I'm a big proponent that we got to reverse aging. We got to telomere repair studies. Aubrey de Grey needs to fund something, because 500 years, I think, is a bare minimum. But feeling like you're 35 and thinking like, having that kind of faculty for 500 years, the species needs it if we really want to survive long term, because I think we need wisdom that we lose really rapidly. And as next new technologies emerge, emerge and young people really are running those technologies, I think that there's an information gap that gets lost. There's this whole law of forgetting that's going on that is really dangerous for our human species overall. So I think it's really important that we address that as well. Also, I'd like to live a long time, so that'd be good.
By the way, can I add another comment? I worked at IBM. I wasn't in that area, but no one expected that they could make these circuits down to almost to the atomic level. That was never even thought possible. So and that's only about 10 or 20 years. We're not talking a large amount of time. What was done in the last millennium is just mind-boggling, where planes were, putting around, and now we have supersonic planes, and we're taking people up into space.
Rockets that land
like
themselves.
Musk is doing, right?
Yeah,
Right.
We're actually on like a vacation.
No, and I appreciate so much the way that private industry is sort of adding, I don't know if pressure is the right word, but momentum. But I also worry that it's a little bit of this, there's a lack of real policy and there's a lack of any kind of checks and balances. And so I don't know, as much as it excites me, there's another part of me that's like, oh God, what is this about to, what's next for us in terms of our dark skies? I mean, the whole constellation satellite stuff, don't even get me started on this, and what an outrage this has been for so many. I'm sure all of you understand this is a nightmare, but there's a lot of situations like this.
I'm curious
Can I
when they
ask
start launching rockets into constellations of 40,000 satellites. It's going to be very interesting to try to find your way through that.
Yep.
Yes, right.
There's a very large volume up there, but 40,000 shrinks that volume and the chance of a collision quite a bit.
And
it's very
Kessler syndrome's a real issue too, where you have this domino effect by one collision hitting another collision. So that is a huge problem as well. Yeah.
I hate to break in right now.
Sorry.
But the meeting is scheduled to end on the server in less than a minute at 9:15. So thanks everyone. Great presentation. It's been great visiting with everyone. And we'll see you next month on Friday, May the 13th. Good night, everyone, and take care. Thanks, guys.
Bye-bye.